ionization energy, electron affinity, electronegativity, covalent bond, polar bond, oxidation number, and the half reaction. So ionization energy, whenever you want to explain or introduce or give the introduction or definition of the ionization energy, it is the minimum energy required to remove an electron from its outermost shell or valence shell in its gaseous state, right? It is always an endothermic process. So suppose you want to uh, take out the first electron or the first ionization energy from this metal, right? Then you will get the metal cation and the one electron is exiting from it. It is always an endothermic process, and whenever you want to remove the second electron from this cation, it is also known as, or it is known as, the second ionization energy. So to remove the first electron from its valence shell is its first ionization energy, and the resultant ion is the cation, first cation. Now if you want to remove the energy electron from this cation, it is known as the second ionization energy. Second ionization energy is always higher than the first ionization energy. The reason behind it, that here you are removing the electron from its neutral state, right? But here in the second ionization energy, you are removing the electron from its already ionic state, or that is the cationic state, right? Now how the trend of ionization energies goes on whenever you are moving left to right in periodic table or up to down in a periodic table. So the larger the effective nuclear charge on the electron, the more the energy it takes to remove it, means how much higher is the force of attraction from its nucleus. It is tough to remove the electron from its valence shell. Then next, how much is the distance from the nucleus? It is easier to remove the electron from it, means if the electron is far from the nucleus, its ionization energy is less. But if the electron is close to its nucleus, the required energy to remove the electron, that is its ionization energy, will be higher, right? So this is the trend of electron and ionization energy of the elements across the periodic table. So what are the various factors which are influencing the ionization energy? The first one is the size. As I already explained you, the larger the size, easier to remove the ion. Effective nuclear charge, lesser the nuclear charge, easier to remove the electron from its valence shell. Penetration effect of orbital. The third important factor is that the order of energy required to remove electron from sp-df orbital is shell is, means if you want to remove from s, the required energy is low, but if you want to remove the electron from its d orbital, the required energy will be higher. Now the shielding or the screening effect. Screening effect result in decreasing of force of attraction between the nucleus and the outermost electron, and lesser energy is required to separate the electron. Thus the value of ionization potential or ionization energy decreases. Now stability of half filled and full filled orbital. As I already explained you about the stability of half filled and full filled d orbital in the module 2, you can easily understand that if you want to remove the electrons either from the half filled orbital or from the full filled d orbital, it is much tough rather than the partially filled orbitals, right? Now stability of half filled and full filled orbital, it is already explained that half filled orbital or full filled orbital is comparatively high in order of its stability, right? So more energy is required to separate the electron from such an atoms, right? Now we are having certain exceptions in the first ionization energy. As I told you, whenever we are moving left to right in periodic table, the ionization energy increases because it is the force of attraction from the nucleus, that is the Z effective, is increasing. That's why it is tough to remove the electron from its valence shell. But in case of beryllium and boron and nitrogen and oxygen, when we are comparing, as you can easily look it out here, if you want to one electron from the boron, this electron is there in 2p, whereas in case of beryllium, if you want to electron to remove, then you need to remove this electron which is there in a 2s orbital, that is the a fulfilled orbital. So to remove this electron in beryllium, is comparatively tougher than to remove this electron in the boron, right? In the same way, to remove this electron in nitrogen is quite tougher than to remove this electron in the oxygen, right? So these are the exceptions in the ionization energy. This is the full explanation. Then here again, so all about the ionization potential or ionization energy, that it is the energy to required to remove the electron from its valence shell, and whenever you are moving left to right in periodic table, it increases due to the increased nuclear charge, effective nuclear charge, and whenever you are moving up to down in periodic table, it decreases because of the increased distance from the nucleus, right? Now the next term is the electron affinity. Electron affinity is just reverse of the ionization energy. There you are just removing an electron. Now here you are just adding an electron to a neutral atom, right? Electron affinity is the energy change when an electron is added to an atom. Now how its trend goes on, again as in case of the ionization energy, same pattern we have in case of electron affinity. As we move left to right in periodic table, it increases, and when we are moving up to down in periodic table, it decreases. Now various factors which affects the electron affinity. The first one is the atomic sizes. As the moving left to right in periodic table, atomic size decreases, right? That's why it is, and the effective nuclear charge is much more, right? So the force of attraction decreases between the electron being added the atomic nucleus due to the increased distance between them. Now effective nuclear charge, electron affinity value of the element increases as the effective nuclear charge on the atomic nucleus increases, because electrostatic force of attraction between the electron being added and nucleus increases, right? Screening or shielding effect, electron affinity value of elements decreases with the increasing shielding or screening effect. We already studied the shielding effect under the Slater rule. The shielding effect between the outer electron and the nucleus increases as the number of electrons increases in the inner shell, right? Now again, as the half-filled and full-filled d orbitals affects the ionization potential or ionization energy, in the same way it also affects the electron affinity, right? Now electronegativity. Electronegativity is a measure of the tendency of an atom to attract the shared pair of electron in a covalent bond. Covalent bond formation takes place due to the sharing of the electrons to each other, and ideally as these two electrons are shared equally by two individual atoms, so the position of the shared pair should be at the center. But due to the higher electronegativity of one of the element, it goes towards the higher electronegative atom. So what is the electronegativity? It is basically the tendency of attracting the shared pair of electron towards itself, right? Now the Pauling scale is the most commonly used to check the electronegativity, and as per that, fluorine is the most electronegative atom, and it is having the value of 4.0, and the values range down to cesium and francium, which are the least electronegative of 0.7 value. Now if the electrons are shared by both these two elements equally, this red is shared by A and green is shared by B, ideally the position should be at center. But due to the higher electronegativity of the B, the shared pair electron moves slightly towards the B, right? And B, therefore, due to the higher cloud of electrons, B generates a slight negative charge over here and A generates slight positive charge over here. So this type of, already it's a covalent molecule, but here it is a covalent molecule which is having the characteristic of ionic compound due to this difference of electronegativity, and this type of bond also known as polar covalent molecules or polar covalent bond, right? Now this is the trend of electronegativity. Whenever you are moving left to right, the electronegativity increases, or I told you that fluorine is the highest electronegative atom, right? Now polarizability. This polarizability concept was given by Fazans in 1923, and it says that you can predict whether any covalent compound is having any certain ionic character. As earlier I explained you that how a covalent bond at AB converted into ionic bond due to the difference of electronegativity between A and B, right? So if you want to calculate any ionic nature or ionic character in a covalent molecule, you need to go through with the Fazan's rule, which was given by Fazan in 1923. Right. When we are bringing out or bringing close to oppositely charged ion, the nature of the bond between them depends upon the effect of one ion to the another ion, that is the polarizability. Here you can see this is the normal non-polar covalent molecule, this is polar covalent molecule. Now due to presence of this, it is converting into this, so it is converting into a polar molecule. So the ability of a cation to distort an anion is known as polarization power, and the tendency of the anion to become polarized by the cation is known as its polarizability, right? The polarizing power and the polarizability that enhances the formation of covalent bond is favored by the following factors. Number first, if you are having a size of cation is comparatively small, then it will be having a high polarization power and it will be having great concentration of positive charge on the smaller area, right? This is the reason why lithium bromide is more covalent than potassium bromide, because the size of the lithium cation is 90 picometer, whereas potassium is 152 picometer. The smaller is the size of the cation, more polarization power of the cation. Now large anion, as vice versa of the cation, larger the size of the anion, more the polarization will be done by it. Now large charges, as the charge on the ion increases, the electrostatic force of attraction of the cation for the outer electron of the anion increases, resulting in the degree of covalent bond formation increases, right? So these are the various factors which affect the polarization or polarizability. Now the redox reactions. Redox reaction, whenever we are talking about oxidation and reduction combinedly, it is known as redox. Red for the reduction, OX for the oxidation. Now if you want to give the definition of the oxidation, whenever it is the gain of oxygen, or whenever it is the loss of hydrogen, or you can say whenever the element is losing the electron, or it is the increase in the positive charge of the electron, it is always the oxidation, right? And whereas what is reduction? Losing the oxygen or gaining the hydrogen or gaining the electron means the decrease in the positive charge is known as the reduction, and collectively these two reactions are known as the redox reaction, right? Now the charge on the any atom, either neutral or the positive or negative charged ion, how you will check its oxidation number. So we are having certain rules to assign the oxidation number of any moiety, any molecule or any complex or any ion. The first rule is that the oxidation number of an element in its elemental form is always 0, right? The oxidation number of a simple ion is equal to the charge on the ion. If suppose it is A plus 2, then the oxidation number of A will be plus 2. If it is A minus 2, then the oxidation number will be A of the A will be minus 2. Now the oxidation number of group A, 1A and 2A is always plus 1 and plus 2 respectively. In compounds, the oxidation number of hydrogen is almost always plus 1, right? But whenever it is combining with the metal, as sodium is combining with the hydrogen, sodium hydride, the oxidation number of hydrogen is plus 1, right? As the rule, as per the rule. But what I told you, 1A is always plus 1. So sodium belongs to 1A family, so it is having the plus 1 oxidation number. So in reverse, what the hydrogen will have, it will be having the minus 1. Right, there's another rule. In compounds, the oxidation number of fluorine is always minus 1. The oxidation number of other halogens, chlorine, bromine and iodine, is also minus 1, except when they are combined with oxygen. Means whenever the halogens are combining with the oxygen, they are not having this minus 1 oxidation number. For an example, if you are having the ClO, right, here the oxygen is minus 2 in general, but here it combined with minus 1. So what it will be having? It will be having plus 1 oxidation number, right? So this is the exception over here. Now in compounds, the oxidation number of oxygen is always minus 2, right? The most common exception is the peroxide, means whenever oxygen is combining with the hydrogen H2O2, it should be minus 2, but here in it is plus 1, so plus 2. So what will be in reverse? It will be total minus 2. So for one oxygen it will be minus 1, right? So here exceptionally the hydroxygen is having minus 1 as oxidation number. For a complex ion, the sum of the positive and negative oxidation number is of all elements in an ion equal to the charge on the ion, right? For an electrically neutral compound, the sum of the positive and negative oxidation number of all element in the compound equals to 0, right? So you can easily understand that whenever you want to do the calculation for the oxidation number, how you can go or how you can do the calculation of the oxidation number. Suppose you have given the example of the this complex and you want to check the oxidation number of chromium in this potassium chromate, right? K2Cr2O7. Now as the total charge on this whole complex is nothing, so it's 0. So the collective or addition of all the oxidation number of all these elements will be 0 only. So 2K plus 2Cr plus 7O equal to 0. We know K belongs to 1A, so it is plus 1. 2Cr, it is the to which you want to calculate the oxidation number. Oxygen is always minus 2 equal to 0. So plus 2 plus 2Cr minus 14 is equal to 0. So as per calculation, what is the oxidation number of chromium? It is plus 6, right? So this is the way how you can calculate the oxidation number for the various elements in any complex or in any compound, right? Now consider here zinc plus 2HCl equal to zinc plus 2Cl negative ion plus H2. Now the oxidation number, here the oxidation number of zinc is 0, here it is plus 2, here H is plus 1, Cl is minus 1, plus H plus 1, H is converting into 0, and this Cl minus 1 is converting into it remains same. So here the total charge of this zinc from 0 it convert to plus 2, means as the charge is increasing from 0 to plus 2, and here the charge on the hydrogen converts from plus 1 to 0, right? Here in case of the zinc the plus charge is increasing, that's why it is the oxidation, and here in case of H it is decreasing, means it is the plus 1 to 0, so it is decreasing. So Zn, the conversion of zinc to zinc ion is a type of oxidation reaction, and the conversion of H plus to H0 is the type of reduction reaction. So here in this whole reaction we are having both the example of oxidation as well as the reduction, so it's a complete redox reaction. But whenever you are writing down only half oxidation and half reduction reaction, then these reactions are known as the half reactions. So you got my point? So this is the half reaction. Whenever you are having the only oxidation reaction, it is half oxidation reaction. Whenever you are having only reduction reaction, it is half reduction reaction. And collectively these are known as the redox reactions, right? So this is all about the third module. Hope you have enjoyed all the terms and concepts what I explained you here about the ionization energy, about the electron affinity, then electronegativity. All these factors and the concepts are very much important when you are learning the chemistry, especially the electronegativity, how a covalent compound is converting into a ionic compound, and you can calculate this characteristic by the Fazan's rule, right? Then the oxidation reduction reactions were there. So hope you enjoyed this session. Keep learning, keep trying. Okay, thank you.